Okay, welcome to the second part of this course of the course 4210. My name is Andy and I will be responsible for this part. So these are the textbooks. If you're interested, you can tap on the links. I have put the links of them here. So most of them, so these two would be what this course is mainly about, the second part of this course. And then if you are not familiar with the basic thermodynamics, you can always refer to this book, Wallace and Hobbes. Okay, and then there is another new textbook that is available. I think it's available from the library. Okay, so in this lesson, we will talk about some basic thermodynamic relations and moisture content in air. So if you have taken 3200, this part would be very easy for you, but I think it's good to have a revision. So before we get to that, I will have a little bit of introduction for the planetary boundary layer that we have in the atmosphere. Okay, so this is a very simple idea. We have different scales in the atmosphere. For example, if we talk about temperature, we'll have higher temperature in the summer and then lower temperature in the winter, right? There's an oscillation. This is yearly. Okay, it's due to the orbit of the Earth. Okay, and then if we magnify this part, we will see that there is also daily temperature variation. So this curve is not smooth at all, actually. So if we look at the temperature for a day, for example, at the noon or around the afternoon, the temperature will be the highest, and then at nighttime it will be the lowest. So we call this diurnal variation. So you can see that there are different kind of oscillations in our atmosphere, and then when we talk about different weather phenomenon, we need to talk about the time scales that we are focusing on. Okay, so if we focus on the diurnal variation, this is the diurnal variation, and then we magnify even more, you can see that it's not smooth at all. Again, we have a lot of oscillations happening, and it's more prominent during the daytime. And it's probably due to there are much smaller and faster variation, and we call the swirling wind turbulence. So the turbulence near the surface, they're mainly due to the thermal energy coming from the surface. Of course, it's energy from the sun. And then also the topography of your surface, it's coming from the mechanical energy. We have roughness, we have orography or topography, different mountains. And then actually we feel the sum of all scales, but in this course we will talk about these very small scales of atmospheric motion. So this one can happen in the daytime and the nighttime because the topography is always there. And this one is more prominent during the daytime because this energy from the sun, so of course it's during the daytime. Okay, I think you are all very familiar with this, so this is for your reference. We have different times and space scales in our atmosphere. So the x-axis here is the daytime, is this time scale, and then this one is the spatial scales. And you can see that different weather phenomena, they are associated with different scales. For example, hurricanes or tropical cyclones is between synoptic scale and mesoscale. And the time scale would be days to a week or more. Okay, and then in this course we will talk about the very small scales. I think it's between mesoscale and microscale, we call them. So it's turbulent eddies in our atmosphere. So they are very fast, they're very small. By fast we're talking about seconds to minutes, and small we're talking about a few meters or a few hundred meters. Okay, so this one is what we will talk about in this course. Okay, so when we study a scale, we need to also focus on the scale above the current scale that we're focusing on. So for example, the mesoscale, which is the associated with thunderstorms, tornadoes, things like that. So they are driving what we have in here directly. So the energy of these turbulent eddies, they are probably coming from the larger stuff, just one level higher. Okay. So in this course we will talk about boundary layer. So what is a boundary actually? So why do we need to talk about boundary? For example, we have a boundary here between the air and the water. You can see that properties change. Some physical quantities change. And then there is energy exchange between the boundaries. You can see that if you have an air molecule bumping on the warm surface, and then when it bouncing back, it will gain some energy from this warm surface because this is cooler, right? So there is a transport of heat between the land and the atmosphere. Okay, so there's also matter exchange. By matter, we are mainly talking about the moisture and also air exchange. There is air in the soil. Okay, so energy exchange and matter exchange. Also, another type of exchange is momentum exchange. We'll get to that later. Okay, so in the atmosphere, we have a layer of air called atmospheric boundary layer or planetary boundary layer, and also known as PBL. Okay, so if you look at the website Windy, I think all of you have seen this. So if you look at the wind directions on the surface and then from a bit higher, 850 hectopascal, you can see that the wind directions, they're not the same because the surface is modulating the wind in this boundary layer. So 850 is just about the boundary layer. It's around the level where we are getting away from the boundary layer. So this is not the exact value that is applicable all the times, but we use this as a reference. Okay, and then we can look at this. I think we can look at this video. Okay, so we have a water tank here, and there's a plate moving in the water. And if the flow is magnified, you can see something very special near the boundary. Okay, so if your plate is moving and then there is a boundary layer near this plate, you can see that there is some swirling wind because your plate is moving, and you can clearly see something, the swirling water, which is something what we call eddies. Okay, I think I'll get back to the slide. Okay, so clearly the properties of this layer is very different from what we call the free atmosphere. By free, we are talking about it's free of the influence of the surface. Okay. So we have different definitions for the different layers. So for in here, first thing we need to know about is that we are defining different layers in the vertical dimension. Okay, because the sun is heating up the surface, and then everything is changing in the vertical dimension. Okay, and we don't talk about the horizontal variation a lot because it's just complicating things some more, okay? We talk about the simple case of homogeneous. This is not homogeneous, but most of the times we talk about homogeneous surface properties, okay? And then we have, first of all, we have the troposphere here. And then we have what we call the boundary layer. This is not in scale, this is in log scale, okay? So the boundary layer, it's actually a very thin layer. And then we have a layer for the exchange between the free atmosphere and the boundary layer. And then we have a layer called surface layer. Don't worry about them. So we will get to the details for these different layers later, okay? We need to know about the significant exchange of momentum, heat, and mass between the boundary layer and the free atmosphere, and then the boundary layer with the surface, okay? And over a longer period, the interactions may span the whole depth of troposphere. So even though the boundary layer is a thin layer comparing to the troposphere, its influence could be transferred up to the free atmosphere. So people say that it's very important to have the right depiction or the right representation of the boundary layer in order to have a better weather prediction or climate prediction for the future, okay? And the thickness of the boundary layer is actually changing all the times. It could be from tens of meters to a few kilometers. So basically, we most of the times we think of the boundary layer with a height of 1 kilometers, but it's actually changing all the times. And it depends on, of course, the rate of heating and cooling at the surface, and then the roughness, and also wind speed, and then also the large scale motion, which is driving the smaller scale turbulence, okay? And here, we are just showing you the near neutral stability. Okay, if you have studied for 4200, we have talked about stability in our atmosphere, right? Don't worry about this. We will have a little revision in this course. So this is like a typical situation for the near neutral stability in the atmosphere. And then the height of the boundary layer, sometimes we call that mixing height, aka means also known as mixing height. It's very important in air quality studies because this boundary layer is trapping the air pollutants within this surface layer, within this surface, the area near surface, okay? And the near surface emitted pollutants are eventually mixed in this depth. So by mixing height, we are also talking about the air mixing around in here. So by mixing, the air properties are also mixing together, then the air properties might probably have the same, the properties might also be the same because everything is mixing in here. We'll also explain more later about this. So this is just a brief introduction for my part of the course. Okay, so the transport of the momentum, heat, and mass is actually accomplished by the turbulent flows. So in here we have laminar flows. Laminar means there is no swirling wind or swirling fluid in the atmosphere. So the straight lines there are all the laminar flow. And sometimes because of a very small triggering factor, then we'll have some instability in your air, and then there will be swirling winds. You can see that there are different, they have different sizes, of course. There are smaller sizes of swirling winds and bigger sizes. We call them eddies. Okay, these swirling winds, we call them eddies. You can see that if you follow just one air molecule, it's actually doing a lot of swirling around. It could be to be swirling in this orange region. So prime means that it's a turbulent flow. We always use this U bar. It could be any direction of wind, okay? The U bar is representing the laminar flow or the average flow, and then U prime is always the eddies or turbulent flow. So you can see that when your air molecule is going into this swirling area, you can see that it could bring the momentum, heat, or mass to different heights. Okay, so basically it's transporting different physical properties around. Okay, so these eddies, they are responsible for that. In this course, we will talk about how strong the mixing or the turbulence can be, and what does that depend on. And then you can see that we have separated the scales into the average flow and the turbulent flow, and the interactions between scales actually can be studied. Okay, so this is like a brief schematic diagram for the boundary layer and the free atmosphere. You can see that there are different sizes of swirling wind. We have big eddies or large eddies, and then we have smaller eddies. It's we have a very basic assumption that the eddies near the surface is smaller because the space that they can move around is smaller. Okay, and then they could get bigger when it's higher in the atmosphere. And then sometimes we will have some air exchange when your convection is too strong. Okay, we call this convective boundary layer because it's due to the convection. There is energy or matter exchange. Okay, and then we have a level where we define the boundary between the free atmosphere and the boundary layer. It's called capping inversion. We'll also get to that later. Okay, and this is a slide explaining to you the difference between the laminar flow and turbulent flow. Okay, in the free atmosphere, we have assuming we have a very steady state of the wind in one direction, and then when it's closer to the surface, it's slowing down because of the surface friction, okay, and it's still a laminar flow. So imagine that somehow you have some type of heating in the surface by the sun or some topography, then there would be some instability produced because of your topography or because of your heating, okay? And then you can see that there is turbulent flow because of that, okay? And then the turbulent flow will have, because of turbulent flow, we'll have some vertical mixing because the horizontal flow it's now becoming swirling winds, and then there will be vertical component of these wind, okay? So that's how we get the vertical mixing in the turbulent flow. Okay, so imagine that we have some area, some urban area, and then we have some very flat terrain, and actually it's affecting the wind profile. So this is the wind profile. You can see that the wind in the higher level is larger, and then we getting smaller because of the surface friction or all the buildings in here. And we have a way to quantify this situation, okay, comparing this and comparing the urban area and the flat terrain. We have a reference value. We call them aerodynamic roughness. When it's larger, then actually it's rougher in the surface, and the smaller it's the flat terrain. Okay, so the mean wind profile. So this is only the mean, which means that it's we are just talking about this one, the U bar. Okay. In this course, it's very important to understand the difference between the mean and the turbulent component in a variable. Okay, next we talk about the concept of flux. It's actually very important because we use this to study the exchange of momentum, heat, and moisture. Okay, so it's also known as flux density. It's passage of some quantity. It could be some volume, it could be some weight. It's the passing of these properties per unit time, per unit area. Okay, so for example, heat flux is the amount of heat passing through a unit area per unit time. So it's a vector because it's passing through one direction, right? So it's in here, the heat flux, the unit of heat flux is watt per meter square. And it could be other variables like moisture and momentum passing through. So in here we have an example, there is a fire here, and then you have some kind of metal, and then the heat is transferring or passing through this metal to your hand. So the amount of heat passing through the unit area per unit time, that will be heat flux. Okay, so because it's direction dependent, if your physical quantity is passing through the area like this, it would be the maximum flux achieved. And in here, no flux is given because the thing is not passing through this area. Okay. So mass flux, the weight of your air per unit area per unit time, and here moisture per unit area per unit time, and flux is energy here, joule per unit area per unit time, and also here momentum flux, this is momentum, right, and per unit area per unit time. So this is the conventional way to study flux, but in this course we talk about the kinematic form of flux. In here we talk about the conventional flux that we have talked about in here. Okay, the original flux divided by the density of air. Okay, and we do that for all of them except for this one. Okay, we divide the moisture flux with the density of air, and then we divide the heat flux with the density of air and then the specific heat of air. Okay, and also for momentum flux we do the same. Why do we do this? Because when we do this, it would be more convenient to compare with the measurements. So in here we can just use the humidity, the measurement from the humidity times the wind speed. Okay, this is exactly wind speed, actually, the unit of this. And in here we can just measure the wind speed and then measure the temperature or the potential temperature. That is already the heat flux. And in here, if we want to see the momentum flux of the horizontal wind U, the vertical momentum flux, we can just multiply the vertical wind speed and the horizontal wind speed. Okay, so the upward or downward motions in the eddies, so this one W is the vertical wind speed. The upward positive W and downward negative W motions in the eddies can affect or can move the heat. This one, okay, it's moving the heat upward or downward, and then also moving the momentum in the planetary boundary layer. So this is how we study flux in this course. Okay, so a little bit about conduction and convection. I think all of you know about the difference between convection and conduction. So convection is the heat transfer due to the movement of your fluid, and conduction is there's no movement of the molecules, only the vibration of the molecules is moving the heat around. Okay, so that's the difference. I have a little bit of the simulation. I provided a little bit of the simulation with this link here, but actually we cannot, I think I cannot get the Java running in Chrome or in any other kind of browser. So this one, if you're interested, you can go take a look. But you have to install. Okay, I'll show you. Okay, so originally we have a simulation in here between the text and then in the panel, in the gray panel. But now because Java is not showing up um, in any type of browser, so if you're interested, you can download the software. So you can see that if you're Mac or Windows, you can download the software, the Windows installer and Mac installer near the orange box here. Okay, you can install that and then you can download the script. Right click to download this model in here, and then you can run the simulation with different conductivity and viscosity numbers. If you're interested, please go take a look. I want to use this to explain the Prandtl number. So the Prandtl number is comparing the heat transfer by viscosity or by convection, okay? And then the heat transfer by conduction. So thermal diffusivity is representing the conduction in your fluid, okay? So by viscosity, you can see the comparison in here. So honey has a higher viscosity and then water has a lower viscosity. So if we have a very high number of the Prandtl number, it's representing strong convective transfer. So the heat is transferred by convection more than thermal diffusion or conduction. Okay. I have prepared the results of the experiment in this link in here. So this is the case where Prandtl number is very, very small. So by very, very small, we are talking about conduction stronger than convection. You can see that at the surface, we have provided a very hot surface. It's around 30 degrees Celsius. And look at how heat is transferred up to a thermometer in here. Okay, it's basically conduction. Okay. Sorry about this. It's basically conduction. And then the next one, the Prandtl number is 1. So, which means that convection is stronger in this case. You can see that when we have a hot surface on the bottom, the heat is transferring up by convection, and there are eddies in this fluid. Okay, so heat is transferring up. You can see the temperature from the thermometer is changing. Okay, so the third case, we have the Prandtl number equals to 100, which means that convection is doing the job of transferring heat instead of conduction. Okay. So in the atmosphere, in the planetary boundary layer, we have a lot of measurements around the world. I don't think we have this, the tower measurement. We have something on the top. We can measure the wind speed and then the wind, and then also the wind magnitude. And then we also have things around 2 meter high. You can see that they have different wind direction. This one is westerly and this one is easterly, so they're in opposite direction, which means that there's something happening, okay, in this boundary layer. So it could be due to some kind of buildings or trees or forests next to this tower, then you can see that it's possible that they have opposite direction because of the modulation of this forest on the wind profile. Okay, so there is recirculation region in here. So in here, if we measure the W wind direction, and then we also have thermometers in here, we can measure the heat flux, right? We have numbers here and then we have numbers here, and it's called the eddy covariance method. So this is the covariance of these two variables, and measure the vertical turbulent fluxes in the planetary boundary layer. We can also measure the flux of carbon dioxide, heat, and momentum. So the momentum flux is measured by these two variables. We do the product of them, we can find out the flux.